this is Dr. S. P. Arsa from Mechanical and Industrial Engineering Department, IIT Roorkee. I'm going to deliver my lecture 14th on the subject of strength of materials, and this, like the course is developed under the National Program on Technological Enhanced Learning. If I just, refresh on the previous concept, then in the previous lectures we had discussed about the main concept of the stress and strains, and you see, when they are all the both components they are applying on this material, then how the material is reacting, and what the stress components are there, and where we can get the maximum and minimum stresses that we discussed analytical and the graphical way. And then you see, we discussed about the two main categories of this material, as one if the ductile material is there, and we also discussed about that what the ductility is there and how ductile material is behaving when we apply the tensile test. So whenever you see the the tensile pulling is there, then you see we define that the stress versus strain curve, and there are two main regions. One is the elastic region and the plastic region, and also we define about, if you are talking about the elastic region, then what exactly the elastic constants are there, like modulus of elasticity, the shear modulus of rigidity, bulk modulus of elasticity, the Poisson ratio. All these are the main constant which can be which are useful and which can be defined in the elastic region only. And once we go to the nonlinear the stress versus strain relationship, that means we are going the plastic region, a permanent set of deformation is there, and in that also we can get the maximum the strength, which is known as the ultimate tensile strength before fracture. And then we are approaching towards the fracture, and if it is a ductile material, like if we have the mild steel or high speed steel or high carbon steel, or we can say aluminum, or whatever you see this kind of ductile material which are exhibiting a good tensile strength, then probably we can say that actually at the end of the fracture we have a very specified shape, generally as we termed as the cup and cone structure, in which you see we have a cup, there is a dip is there, and there is a cone kind of that, where you see there is an extension gradually reducing portion is there. So this is, you see as well as the ductile material is concerned under the tensile test. And if we apply the similar kind of tensile test on the brittle material, then we would find that you see that we have the linear region and between the stress and strain, where you see the proportional limit is there, and Hooke's law is valid for that. But the plastic region is very, very small. So once you leave from the yield point, then immediately we found that the fracture is there, and there is no specified shape as far as the brittle material is concerned under the tensile test. So this kind of the information which we captured from the tensile test, and if we are conducting the compression the compressive test on the tensile on this particular ductile material or on the brittle material, then we found in both of, you see, either under compression, if the ductile material is there or brittle material is there, the linear region is the similar as the tensile test. That means you see, even if you apply the compression or even if you apply the tensile, then there is no change in the linear region, and all those parameters is well applicable for both of both material under all conditions. So that's why you see in the numerical problems, if you found that okay, this material is under consideration of the tensile test or the compression test, then always you can apply if it is going beyond, you see, the yield point, then we cannot apply all those constant which we discussed, like the Young's modulus or shear modulus or bulk modulus or Poisson ratio. But if it is within this range, it means the elastic region range, then it would be preferable to use those elastic constant to get the value of the stress versus strains, and we can say, you see, we can get all those the values of the maximum or minimum stresses within that object. So this kind of the relations which we set up for the ductile as well as the brittle material, if it is under the application of tensile test or under the application of compression test. And also we would find that actually the mild steel, or we can say the ductile material, if you want to capture the ductility of property, then always the elongation will be the key feature. So how much elongation is there, and always we put the limit that if you want to go for ductility, then it should be starting from the 10% to 40% of the limit is there. So that kind of, you see, the ductility, if you want to see in any material, we can use those information. Then another point which we discussed about the elastic range, that what will happen under the elastic action. So that's what you see, there were 4 graphs which we discussed in between the this stress versus strain. So this again you see like the important information was there as far as the ductile property or the brittle property of a material is concerned. Then also you see apart from the stress, strain, ductile, brittle, then there are some other properties which are very useful to choose a material for engineering design, because if you want to design the things, then the only the material is ductile or material is brittle is not at all sufficient. Then we would go for the another property, and those properties are the hardness. Then you see like to measure the hardness, we define the hardness that it is like the resistance against the penetration. Then there are some methods like you see the Brinell hardness testing machine was there, the Rockwell hardness testing machine was there, even the Vickers hardness testing machine was there. So all three are applicable, but they are applicable in the different reasons, because you see in the Brinell we had used like that steel ball was there as a penetrator, and the material is like a specimen of any kind of like either the steel or the less harder material as compared to the indenter. But there were some like disadvantages were there. So probably like it is not acceptable that because of any truncation error or because of any like the geometrical deviation of indenter, if we are getting not exact value of the hardness, then it is not preferable. Then always we are using the Vickers hardness in which the diamond point is there. But again like the biggest disadvantage in that was like diamond is there, and we just want to avoid the damage of the diamond because it is very expensive, and even it is not safe to keep all those diamond points like for this kind of application to check the hardness. So you see preferable one is the like the Rockwell hardness is there, in which like the conical shape of indenter is there, and you see since it is a conical shape of 120 degree of like the shapes are there, so it is preferable to use in industry. And since you see we are only measuring the depth of penetration, and based on that actually we can calculate the hardness, so it is preferable to use the like this Rockwell testing machine to check the hardness. So these three kind of like the hardness testing machine was there. And then we discussed about the toughness. Toughness is nothing but like if you just refresh those things, then it is nothing but the whatever the cracks are there in any material where the strength concentrations are there. So it is the property of a material through which material shows the like the strength against the impact loading. So whatever the energy which material can absorb against the impact loading, that is nothing but the toughness. So it is always you see preferable to get the value of the toughness if we are using the Izod-Charpy test, or even the Izod test is there. Then there was another like the property was there, that is the creep. Creep is nothing but you see when you apply the load, and if it is a constant load, then again you see because of the surrounding temperature or the high temperature reason, like you see if you are using turbine blade or nuclear reactor or this kind of like this generator is there, or any turbine part is there in which the steams are there, boilers are there. So wherever if we are talking about the material which is under the application of high temperature region, then even the load application is same, or the stress formation is similar, but due to the temperature variation, the thermal stresses are being set up in the material are so high that even like no load condition, but it will start from the strain hardening and it will end up with the fracture of the material. So this kind of failure always comes under the creep phenomena, and even actually we have shown like the previous lecture that actually there is a standard creep curve is there, which is like drawn in between the strain versus time. So how you see time plays a key role in that, and how we can display all three regions of the creep, three types of the creep, like first creep, second creep, and third creep, and how they are like behaving. Means if you want to calculate like the any strain or strain hardening, or you see within that actually the stresses, then how the tangent and how we can draw the tangent and how we can get those value. This part particular we have discussed in the previous lecture. So you see like if you found that, then we had enough information now to analyze the problem. So now we would like to go for if a material which is not the idealistic way, that means you see if you have a material which is under the application of tensile load, and you see more than one load is there, or even you see like in intermediate part of the any specimen, if different kind of loadings are there, then how we can analyze those parts especially. So that kind of like the information which we would like to discuss in this lecture. But again you see the key part is that actually first which material is there, and what are the like the application of the load is there within those materials, and corresponding stresses and strains are coming. So if we see that actually there are some members which are subjected by the uniaxial stresses, we would like to see that actually how the stresses are being formed if the more than one load is applied on a particular metal, and then how the stress and the strains are there at the different locations. So here you see like we have the members which are subjected by the uniaxial state of stress, and for prismatic bar, as we can see in this particular diagram, this particular we have a prismatic bar, and at the two extreme corners of the bar the tensions are there, means the tensile axial forces are there towards the outward direction, and due to this load application we have an extension, and this extension can be measured by, you see, the delta. So this is the delta 1, this is, you see, the total, I should say the gauge length is there, and whatever the elongations which are coming, it can be easily computed by the stress versus strain. So you see we have the delta, which is nothing but equals to the PL by AE. P is the applied load is there, L is the total length divided by the area, A is the area of the prismatic bar, and E is the Young's modulus of elasticity. So whatever the load application is there, we are going up to, you know, like the elastic deformation. We apply the Hooke's law. With the using of Hooke's law, you see, you know, like just put the relationship, the sigma is the stress is equals to E into strain, that is epsilon. Put the sigma value F by A equals to E, which is the Young's modulus of elasticity, into the this epsilon, which is the strain, which is nothing but equals to the delta by capital L. So you can compute this delta L, which is nothing but the deformation due to this application of load axial. Okay, so this is there. Now suppose you see, you know, like if this bar is at one or more intermediate position, that means, you see, if we have a bar which has a different segments, then you see this equation can be easily, you know, like easily adapted to the you know, like just to handle this particular kind of situation. Means, you know, like if we have, as I'll show you the figure, that actually if we have, you know, like the kind of total bar in which there are the parts, we can say A, B, B, C, C, D, and you see, you know, like the another some elongations are there. That means, you see, what we are doing here, we have a uniform bar, as you have seen the previous figure, that was the uniform cross sectional bar, no separation is there. But if we have a bar in which there are some segments, and the segments, you see, there is a close connection is there, and if we are applying the load, then whatever the elongation or the, you know, like the shortening, if we are applying the, you know, like the extension, or if we are applying the compression, then we need to take the elongation as well as the compression separately, and then you need to, you know, like simply, if I am saying that in the AB part if you have a delta 1, in BC part if you have a delta 2, and in CD part if I have a delta 3. So what I need to do, I need to calculate the deformation separately in separate segments, then some delta 1, delta 2 and delta 3 to get the total deformation in terms of elongation or shortening of the total bar, deformation of bar. So you see here the meaning is pretty simple, that actually it has the same algebraic part as you see, you know, like we have the, if we have a uniform bar. So we can either segregate those part in terms of the uniform deformation, or we can simply sum up, you know, like what is the total load is there at the end, and how we can sum up those things, and how we can get the total deformation out of the entire length of this this prismatic bar. So you see here we have, you know, like the kind of as we discussed that whatever the prismatic bar is there, the total segments are coming in terms of dl. So you see here the d del, which is nothing but equals to px dx divided by E times ax. Meaning is pretty simple, that if we have a small segment, even if it is the tensile loading is there, it can be easily, you know, like the load applications are there in the axial part, because it is a uniaxial loading is there. So px is there, and then you see what are the small segment is there, that is the dx segment in terms of the area. Ax is there in terms of Young's modulus, we have E. So if you want to compute for entire region, that means, you see, if I want to just get that what is the total deformation is there for whole prismatic bar, integration is the perfect method. So delta is nothing but equals to 0 to L, which is the total length starting from 0 to entire L, equals to px into dx divided by E into ax. So meaning is pretty simple, that actually whatever the load is there, axial force is there, and whatever the cross sectional area is there under the area of concern, means whatever the matter is there in that, and the load application is there, what we need to do, we need to go for the individual, you know, like the load application, and then we need to sum up those things. So if the expression for, you know, like px or ax are not too complicated, then the integral can be, you know, like found out, and through integral we can get the analytical solution. Or else, you see, you know, like some of the numerical these techniques are there just to, you know, like if you have any complicated part is there. So what we can do here, either we can apply the Rangakuta technique, or even if we can apply the Newmark, or there are tons of numerical techniques are there through which we can get exact, you know, like the deformation, or we can say we can get the exact stress and strains at a particular locations. So these are the key, you know, like the features in that which we would like to, you know, like maintain for a uniform prismatic bar. But now here you see, if we don't have the uniform prismatic bar, means, you see, we have a bar which doesn't have the uniform cross section, a non-uniform cross section is there, then how we can get, you know, like the stresses and the strain at the different sections, that we would like to discuss. So now here you see, here we are considering a non-uniform bar, okay, which has a cross section as shown in this figure, and the tensile load is applying at the extreme end. So here you see here what we have like this prismatic bar which has a non-uniform like the cross section. So the cross section at this is a tapered section, the smallest area is there, and as you move further it has a symmetric extension towards the x direction. So we are ending up to this part, so total length is L, again similar. And if I am just cutting a section particular at, let us say, x distance from the left end. So from this x distance, if I have this section which has the total like the width is dx, and if I am just simply making the section of that, and I just want to find it out that what exactly the stress or what exactly the deformation is there under the application of this load, then what I need to do, because here this area is not at all like the constant throughout this extension. So here you see this length is like small and this length is bigger high. So what I need to do here, I need to maintain like, because the stress distribution is also not exactly similar as we have seen in the previous uniform prismatic bar. So here I need to apply some other technique here to get those values. What here the A is, which we have discussed here, nothing but the cross sectional area of bar chosen at XX sections. So sigma is nothing but equals to P by A, where here A which you need to calculate separately for the different shape of the this prismatic bar. So here E is nothing but, as usual, you see the Young's modulus of elasticity, and since we are applying the load within the elastic region, so obviously this E is well defined for those like section, and if I just cut the section at XX, it can be easily calculated with the using of the stress calculated and the strain measured. So strain is nothing but equal to sigma by E, so it can be easily coming through this particular formula. Then you see whatever the extensions are there in that, due to the application of load, it can also be measured, because if you know the strain, you can get the strain is nothing but equals to the change of length divided by the original length. So what kind of deformation is there under axial load? So this deformation into x, the del x, is nothing but equals to this epsilon, because epsilon will give you the real feeling about the strain, that what exactly the distortion or the deformation is going to on in that particular prismatic bar. And then you see like if you know the original length, then you can easily get that sigma divided by E into epsilon, or whatever the undefined parameter is there, you can easily put those things and get the another value. Meaning is very simple, only the change is there, the effective area under which this load application is there. Once you know the area, you can easily get the sigma. Once you have the sigma, you can get the value of E. If you have the VE value, if you have the sigma value, E is nothing but the property of material, so you can easily get from any of the standard graph, and then you can calculate the strain. Once you have the strain, you can get that the deformation, that how much deformation is there. Once you have the deformation, you can easily correlate that actually what exactly like the distortions are there under the application of the load. So this kind of analysis can be easily made once you have all those parameters with you. And then you see once you apply the original length, then again it is nothing but equals to P by E divided by P by E into delta x by A. And if you want to get the extension, you see the total bar, then nothing but what you need to do, just the small, as we assume that actually this total bar is the summation of all the small segments. So again delta is nothing but equals to integration, because integration is a perfect way to get the final exact solution using this analytical method. So again we are trying to applying like these kind of technique to get the final solution. So delta is nothing but equals to integration 0 to L P by E into del x by A. So if I want to get the extension of the entire bar, it is pretty easy, and it is equals to P by E, because P is load, E is the modulus of elasticity, and they are constant in nature, so they will come out, and integration, because what the changing is there, changing in only the delta x. So delta x, delta x, delta x, so all those small segments, they have the different width is there, because it's a non-uniform bar is there. So what we need to do here, we need to calculate integration 0 to L delta x by A. So and corresponding you see like the deformation will come of the whole. So instead of doing like the small portion and get, you see what the delta 1 plus is there, delta 2 plus is there, what we can do here, we can straight away apply this integration method. So either direct method or integration method, both are applicable. If you see the like the shape is not too complex, it's pretty easy to apply the integration. But if shape is complex, then you see we need to divide the shape into the proper regular like the shapes, and then you see calculate the different deformation for these well specified regions, or we can say the well defined region, and then some of those things, and that is known as the summation method or the direct method. So both methods are applicable, depends on what kind of shape is there and what kind of load applications are there. So now you see, come to the main point again. So let us, you see, the example is there when the, you know, like the bar is tapered. As usual, you see some tapered bars are there uniformly from the d at x equals to 0 and capital D at x equals to 1. Means you see, at initial point we have a, you know, like the tapered bar, that means the small diameter is there, that is the small d, and at extreme end, that means at x equals to L, we have the diameter is capital D. So you see the total length is L as it is showing, and then again we will go the previous action, that actually in towards the x direction, because the load is applied along the x axis. So what we are doing here, we are just cutting the x action, okay, along, you see, you know, like the x axis. So what it is there at the x axis, right from the d, this d, or we can say x equals to 0, we just cut the section which has the width is dx, and it is, you see, the total length right from this is this, you see, as we can simply shown by the this shaded area. So what it is there, you see, if you just, you know, like trace those points, then you will find that this area in this particular figure, the cursor is showing this is the diameter small d. So as it is, you know, like cutting those things, then probably you see we will end up here is d by this capital D, which is the this final diameter. So capital D minus small d by 2. So this is this portion. This portion is again, you see, we have the distance is capital D minus small d by 2. So once you have these two portions, this is the standard right angle triangle. So you can get, you see, the required information, because this distance is nothing but the L. This distance is d minus d by 2, and this is the 90 degree. Okay, so you can get, you see, the required with the using of the trigonometric relations, one can easily get the required extension. So now you see, as you apply the load, what will happen, the extension will be, you know, like there, and extension will be there along the x axis. So here you see this at these particular directions, you will get the extensions. And if I am saying that this is the k distance, k is nothing but, you see, you know, like here I am cutting this plane, whatever you see this particular, you know, like the structure is there. If I am cutting from these things, then this distance from the center region, you see, if I am saying that the k, then what the impact of the k is, because if I am cutting from here, if I am cutting from here, the k will vary. So what I need to do here, instead of, you know, like cutting this section at a small segment, what I am doing, simply taking the uniform, you know, like region, you know, like just take a small segment, find out what the deformation is there, apply the integration right from x equals to 0 to x equal to a, and you see here at x equals to 0, what we have the small diameter d, at x equals to L, we have the capital diameter this d. So all those, either small diameter or bigger diameter, both information which we have at x equals to 0 and x equals to L, and also what we have two triangles, right angle triangles at these two corners. So with the using of this information, we can easily extract the total deformation by integration technique. So you see here, so in order to compute the, you know, like the value of the diameter of a bar or any other undefined parameter, what we need to do here, simply, you know, like using those similar triangles as I shown you. So with those diagrams, d minus d by 2 was the base of the diagram, which was pretty same. Length of the you know, like the triangle was again similar, so it was L. So d minus d by 2 divided by L, it should be equals to k by x, or we can say that actually k is nothing but, k was, as I told you, the distance was there from the center distance to the this particular tapered bar at a particular distance, which we have taken the x region. So we can say that the k is nothing but equals to d minus d divided by 2L into x. So now you see what you have a distance which is known as the intermediate distance, which is, you see, you know, like as you move further, this distance will vary accordingly. And how it will vary? It will vary by d minus d. You see here, if you see the formula, it will vary that how much difference, what is the exact difference is there in between the major diameter and minor diameter, and also it will vary with the x. As you move further with the x, it will vary accordingly. So you know, like the diameter y, whatever you see it is there in the x action, we can get the d plus 2k, or we can say y, which is, we are saying that the diameter is nothing but equals to d plus 2 times of, you see, so 2 will cancel out, so d plus d minus d into x divided by L. So now you see what we have a diameter in terms of the this two small diameters. So the total, we can say the average diameter is nothing but equals to d plus d minus d into x divided by L. So you see, as we move further, then we will find that since we are talking about the x, you know, like xx cross section. So for that the area is nothing but equals to pi by 4 y square, and you see since we know that what the y is, so we can simply say that it is nothing but equals to pi by 4 d plus d minus d into x by l whole square. So once you sum up those things, so now what we have the effective area, that exactly which is affected by the application of load and how the deformation will take place. Now we will go for that. So the total extension of the bar will be given by delta, which is p by a, as we have seen in the previous derivation, that p by e into integration of 0 to l d del x by a. So now you see if you keep those values there, then probably we have delta is nothing but equals to 4p divided by pi e, because the area is there pi by 4 square. So this 4 will go on top of that, this e value, okay. So 4p by this pi e into 0 to l, because at x equals to 0 we have a small diameter, at x equals to 8 we have bigger diameter. So integration of 0 to l into del x divided by this whole this area, what are the area will come. So it is, we have this small d plus d minus dx by l whole square. So now what we have the total deformation in the bar if you apply the load in towards the x direction. So instead of going for the small segments, and instead of calculating the different deformation and then some of those things, it's better once you have a symmetric geometry, cut its section, take a portion, in the portion just see that how the variations is going on. Once you have the variations within that structure, integrate those things right from beginning to end, and then get the value of the total extension, and that's what it is here. So now once you have after the integration, what we have, because we know the values at both the point 0 and l, so we can simply get the final value of the deformation, that is 4 by pi into p into l divided by E is Young's modulus of elasticity, d is the capital diameter of measure, and d is the small diameter. The thing is that whatever the information is giving in the problem, like you see the load is given to you, the deformation is giving to you, or Young's modulus is always there as per the material selected, and if any of the diameter is given to you, then you can calculate the remaining parameters, that exactly. So this information is very fruitful to design any of the material for any the application when the tensile loading is there, because we have the total load. We also have, you see, the specified shape of this any material. Once you have those things, once you have the material, then you can calculate that actually if you apply this amount of load, then probably you will be end up at this kind of deformation, and then you see you can safely design those things. So an interesting problem is to determine the shape of a bar which would have a uniform stress in it and under the action of its own weight and the load P. So now you see in the next segment what we are going to discuss now. Till now you see we didn't select what the weight effect is there. So now if we will go for further, then it would be very interested to see that actually if a weight is there and due to its own weight, what kind of extensions are there, and with those extensions how the stress formations are there with the interaction effect of an external applied load. Because you see what will happen, we have the segment due to its own weight, you see it is going towards the center of gravity, is always towards the downward directions. So the stress formations are there, load application is there at the extreme ends. So because of that the stress formations are there, then what the interaction effect is there of these two segments we would like to see, and that's you see like the next figure we would like to see. So this figure clearly shows uniformly the tapered bar which is hanged vertically. So now we would like to consider the weight of that. So in that what we are going to do, this this is hanging at this particular position. This is, you see, the symmetric geometry is there, and at the extreme corner you see this load is applied. So once you apply the load, you see we have two different components. One, we are considering here the weight, and due to the weight you see this area is also affected. That means you see the center of gravity as it somewhere in this particular location is there where these two the center lines are crossing, and now at this particular section we would like to see that what the impact of the weight as well as the external applied load is there. So this form can be easily continued by taking again the similar kind of analysis, that just cut this particular section by the x-axis. So now we have this particular effective area, and we would like to see that actually how this effective area is being distorted or the deformed shape will come due to the application of load. So what we are doing here, again we are taking the same delta x as the unit width of those things, and it is occurring at right from this particular corner, which is the tapered corner is there. So if you are taking this x distance right from this, we have the delta x, and those things, this area, this is the effective area which is shown here, and this is the effective area where this particular load application is there. So these two areas are clearly showing that at one point we have the self weight, at one point the external applied load is there. So now if you are considering the weight of the bar, which is supported under the section of this x here, this clearly this arrow is showing here, is nothing but equals to integration of 0 to x, because what we are taking here, we are taking the small segment of that. So now we would like to see that actually how these the variation is there of the stress or any kind of the extension within this particular structure 0 to x. So 0 to x is the integration of 0 to x into the density, because now we are considering the weights density, into the gravitational acceleration, because the weight is acted towards the downward direction due to the gravitational acceleration, into the area into dx. So now you see what we have now the weight, and due to this weight we have an extension. So we would like to see the impact of that. So this rho is the density, as I told you. So now we can see that what the stresses are there due to this. The stresses are nothing but equals to P, which is the external applied load. It has a uniform the magnitude is there, plus the weight. So weight is nothing but, as we have discussed in the previous part, that actually the rho into z into this the area, because you see if you are considering the mass is nothing but equals to density upon volume. So whatever you see from those component, we can easily computate that what exactly the weight is there. So rho z a into dx integral 0 to a divided by whole area. So now this is the total load external applied plus weight divided by area will give the stress, or we can say that if you multiply those things by the manipulation, what we have, the sigma the stress due to the combined the applied load and the applied weight, sigma into a is equals to the applied load P plus integral 0 to x sigma z a into dx. So now you see if you differentiate those parts by taking dx into 0 to x, so what we have sigma into dA by dx by differentiation. So once you apply the differentiation, this will gone, because it's a constant value, there is no variation as such with the x distance towards the vertical direction. Then what we have sigma g a, okay, because dx will be integrated. So now we have an equation which will clearly shows that actually how the area is varying, because you see dA by dx is nothing but the variation of area in the x domain. So how this area interception is there all across the body due to those load application, we would like to see. So sigma into dA by dx is always gives you this rho into z into a. So now you see with the same previous equation, what we have dA by a, the change of area divided by original area, which is equals to this rho, which is the density of bar, whatever the material which you are preferring. Here, since it is the extension is there, tensile load is there, so always we prefer to use the mild steel component or any ductile material. So tau is nothing but equals to it will come on the denominator side. So sigma is there, you see. So what we have rho into z divided by sigma into dx from the previous figure, which will give you dA by a. Or if I now integrate those, that you see for a small segment which we have taken for a small x segment or other segments also. So if you integrate those things, what we have integration dA by a, which is equals to again density into gravitational acceleration divided by sigma, which has a constant value, into integration of dx. So now if you are doing those things, it is pretty simple that actually logarithmic is there. So log of e to the base, log of a to the base a to the base e is equals to density into gravitational acceleration divided by sigma, which has a constant value, plus c. So if you put the condition as usual like that, if you have at x equals to 0 at the bottom, you see where the load application is there, we have a equals to a0. So what we have the equation a by a0 is nothing but equals to e to the power density gravitational acceleration into whatever the total distance which we have taken, you see if you see the previous part, x divided by sigma. So now you see the original area or the effective area, now we have both the area and the ratio will give you the exponential component. So now again, if I just reverse that component that you see just hanging out the below, and it is simply going towards the top, then it's all just reciprocal parts are there. The load application is compressive now. In the previous case it was tensile, compressive load is there, and we are considering this area is A0 as I discussed, and this area which is you see like at the self weight, this area is the effective area, and the A by A0 we have discussed that actually it was nothing but equals to exponentially this density into you see the gravitational acceleration into x divided by P. So now if I have this reason that if it is I have just like reverse this phenomena, then I have the compressive load, and due to that you see like we can say that the sigma is nothing but equals to P by A0, because the A0 is the effective like area under like the load application is there. So since this is the effective area under the compression load, so I need to take the compressive stresses at this particular stage is nothing but equals to this P by A0. While if I am going for the x-axis section, then we have you see the this ratio of the area A by A0, which will be nothing but equals to, in this case, exponential terms e to the power say this density of the material, which whatever the material which we have taken here, gravitational acceleration which is going towards the downward direction here, into you see the x, this distance which we have taken the x from the applied load to the self weight this center, and we have you see like the A0 which is you see this effective area at that particular end divided by the load. So you see the same results even if we are getting like if I am just like putting the downward direction, if I am putting like the upward direction, there is no change, only the load application will change here. In that term you see what we have, the nature of the self weight and the applied load will be in the extension part, or we can say the tensile loading is there, and in this case you see we have the compression loading. So it's pretty easy to calculate both in respect of only plus sign will come in the tensile, minus sign will come in the compression of load. So you see here now we would like to calculate some of the numerical value, that so that actually this refresh your like the basics of the formula and how to apply those formula into the real problems. So first of all, the statement of the problem says that we have a round bar of length I of length this you see, and that it is tapered uniformly from you see the radius r1 at one end to the radius r2. That means you see like we have the two different radius as usual, because it is a uniform like extensive bar has a taper shape at these two extreme corners. So now you see show that the extension of like due to the tensile load production, we have you see some sort of extension, and we would like to find out that this extension is nothing but equals to PL divided by 2 pi E R square, where you see nothing like this R2 is equals to 2 times of R1, and like means this final extension R2 is twice of the previous R1. So you see what we have nothing but like at a small segment, this is bigger segment, and this you see if I connect those things, doubled of those things, we have this kind of uniformly tapered bar, and we are applying the extension. So we would like to see that actually how these extensions okay will take place, and how what is the magnitude of this extension is. So now you see like same like if you trace this problem in the real figure, then you would be having this the small r as I shown you, this is the bigger r which has a doubled of this r. Now the same this extension is going on right from this particular like the center line. So as you are simply extending these parts, then probably you will be end up with like the kind of extension. So if I am taking that at x equals to 0, this part is there, like this base is there, I just like I need to take the x section which has like the uniform this thickness is there, that is the dx. So this dx will be calculated here. So I have a uniform like this sort of thickness is there all across the x axis. So this dx is there, and now what I am doing here, I am taking you see the distance right from here to here, the x, the total length is nothing but the L is there. Now I would like to see that actually what exactly the relation is, because this is if I am saying that this R1 is there and this is my R2 is there, then the relation of R2 and R1 is nothing but equals to, it is the doubled of the small radius. So now you see like if I just apply the concept here, then what I am having, just you see like considering those figures, I have R1 like will be the radius of the smaller end, and R2 will be the radius of the bigger end, it is doubled of those things. So now just taking the linear relationship, because it is like uniformly distributed all across the entire length of this particular uniform bar. So if I am just taking those things, then I have the radius at the big this smaller end is nothing but equals to like this R1, first smaller end R1 plus this you see the intermediate position, which is nothing but equals to x by L. X is the distance, L is the total distance of that. So x by L is the non-uniform like this non-dimensional parameters there into what the difference of these two radiuses. So r1 plus x by l, because x is the distance of that small segment, l is the total, so x by l into r2 minus r1. Or I can say that if I am taking that this the k is nothing but the constant which is equals to r2, this r2 minus r1 divided by l into 1 upon r1, then I am having this r1 plus r1 into 1 plus kx. So now you see, if I am keeping those things, and if you want to find it out that what will be the stresses are there, then it is pretty simple that I have the radius, the intermediate radius, where you see I am considering the delta x as a portion. So p by pi by 4 a square. So again you see, if I am going for this that what the diameter is there, then it is easy, or if I am going for the radius, then it is pi r square. So by considering those things, I can easily calculate the radius is like these things, that if I have a uniform section there, then what the stress the distribution is there and what the extensions are there. So the stresses are nothing but equals to, since it is a tensile stress, so it is nothing but equals to the load divided by pi into r square, which we have calculated, r square into 1 plus kx square. So you see, this will give you a clear cut picture that actually if we have the two different radiuses and if we are not considering the weight, then how you see in the all different radiuses are giving the impact, and also with that actually where we are considering the x. So right now you see, like the stresses are nothing, this is not a total stresses, this is just the stresses are there at the xx component. So now if I sum up those things for the entire region of the bar which has a tapered bar, then you see we can again go further that what the strains are there once you have the stress. So strains are nothing but equals to stress divided by E. So you see here P divided by E into the entire area. Or we can say if you want to calculate the deformation, for that now you have the strain. So probably you can, if you sum up those things for the entire region of this particular uniform bar, then it is nothing but equals to 0 to L, because you see we started from 0 and we are going up to the end, intermediate position was the x. So 0 to L into P times of dx divided by E pi r1 square into 1 plus kx whole square. Or we can see if we integrate a simple method, then you simply take, because this is the multiple of the x and we are integrating with the dx, so just take it on the top of that. So probably we will have we have p by e pi r1 square into 0 to L 1 plus kx to the power minus 2 into dx, or if we have minus 2, then minus 2 plus 1 divided by minus 2 plus 1. So we will be having p into L divided by E times pi r1 square 1 plus kl, because again you see now if we need to put the this x in terms of the L. So you see here minus sign will be cancelled out, so we have this much this extension. So you see now go back to the relation, then what we have 1 plus KL equals to R2 by R1, or what we have the total extension. If we are keeping those things, then it is nothing but equals to PL divided by E, E into pi times R1 R2. So that's what you see, we would like to just put those conditions, and after putting those conditions, you see now if I just want to compare the expansion by keeping the case where you see the special case was given that R2 is 2 times of R1, then you see what we had PL divided by 2 pi E R1 R2, and if you are keeping those things, then we have PL divided by 2 pi R1 E times of R1 square. So in that we found that actually whatever the extensions are there, it is due to the applied load, whatever the extension is there, and also the R1 is there, that means what the smallest region of the segment is. So these two are the influencing parameters are there, and we have to be very careful that actually while selecting those things, that what the extension is there and how this extension is taking place due to the applied load as well as the smallest region of that particular segment is. So now you see if you want to calculate, because what we have taken the x segment in between the taper bar. So again we would like to see that what the mean radiation of the taper bar is. So the mean radiation is nothing but equals to 1 by 2 R1 plus R2, or we can say now if I am keeping R2 as this thing, so what I am having 3 by 2 R1. So therefore if we have a uniform bar, the extension of the uniform bar is nothing but equals to the original length into strain, or we can say if I am keeping original length as L, strain is sigma by E. So now you see by keeping those derivations in that particular formula, we would be ending up with the deformation is nothing but equals to sigma by E into L, or we can say whatever the extensions are there, simply keeping those the responsible parameters to see the value or see the significance of those things. Now what we have L by E into P divided by pi which we have calculated 3 by 2 r1 whole square, because r2 which we have calculated, that is nothing but equals to the mean radius which we have calculated is nothing but equals to 3 by 2 r1 square, 3 by 2 r1 is the whole square. So now if I am like generalize those things, then I am ending up with the deformation is nothing but equals to the 4PL divided by like G times pi E into like this pi r1 square. Hence if I just want to find it out, that if I have a uniform bar as I discussed recently, and if I have a tapered bar, then what the difference is? The difference is pretty simple, that if I am talking about a tapered bar, then the influencing parameters are the load applied as well as the smallest segment of that parameter R1. And if I am talking about a uniform bar, that means there is no taperedness is there, simply I am going for the middle portion, for the intermediate position is there, then you will find that you see here not only these positions, you see 4PL is there divided by you see G times of pi R1 square. So both are the responsible parameters to like see that if we have a uniform bar or if we have a this tapered bar. So now you see like if I just calculating you see this comparing those things, then what I have this the extension of in this uniform bar divided by extension of this bar is nothing but equals to 8 by 9. That means you see like you can easily compute that what exactly the total extensions are there in the uniform as well as the tapered bar. So in this chapter what we have discussed, we discussed that actually if we have a uniform bar, then what kind of extensions are there, which are the influencing parameter, and if it is you see now like this uniform bar is extended by its own like weight, and if any external this applied region, the external applied forces are there, then how to get the total stress distribution as well as the deformation. And also we discussed that if we have a total like the elongated bar, we can easily calculate it by just separating the individual sections and just calculate the deformation for individual sections, sum up those parameters and get the final deformation of the entire length of the beam. So this was you see like we did it for the uniform bar, and if I have a uniformly tapered section, that means you see like it is uniform, cross sections are there all along varying to all along varying with the x axis. So what in that what we need to do, we need to just take you see the small segment right from like taken a specified reason that okay, right from like the left corner at x distance, if this particular portion is there, cut that portion, see that actually how the deformation is taking place due to the load application and how the stresses are being set up in those regions, and due to the stress and load application we have deformation. And once you get the deformation for the specified region or the small segment, sum of those small segment for the uniform tapered bar, because you see in the uniform tapered bar only the variation is the area is there, that when the area is changing, load is same, so stress will be different, and if the stress will be different, definitely the strains will be different. So sum of those small segment, once you have the like sum of those things or integrate, so the we are either we can adopt the sum of positions or we can adopt the integration of that. Once you have the total integration of that, you have the extension of the entire uniformly tapered bar. So in that you see segment we discussed the two main things. If you see it is horizontally put the condition, then nothing axial loading is there. If I am keeping that that uniformly tapered bar as a vertical position, that means the self weight is there. There are two types of load application, self weight and the externally applied load. Then you see like you need to add both the component, external applied load and the self like weight, add those things, see the effective area, that at self weight which is the effective area, at external load application which is the effective area, and when you sum up those like the loads with this effective area, you will be ending up with the summation of the two different stresses. Once you have the stresses, you have the Young's modulus of elasticity, you can calculate the strains. Once you calculate the strain, you have the total length of the bar, you can easily calculate the change of length, that means the deformation. Once you have the deformation, now you can either distribute those deformation to different segment or you can simply compare those things, and that's what you see like we discussed in the entire chapter. So you see like in this chapter the total orientation was on the stress and strain with the this distribution under the elastic components. But in that you see like what we assume that whatever the load application is there, it is uniformly distributed all across the element. But if I am saying that this load is like distributed, even the load is distributed at different segments, means if I am saying that I have a uniform bar, and in this bar you see like for this particular segment the load application is 10 Newton, for this segment 20 Newton load is there, for this segment 30 Newton load is there. So if the different segment is experiencing a different loads, then what kind of deformation is there, and how you can sum up the deformation like for calculating the entire like the deformation for the entire beam. That is really a matter of interest, that how the like different load will play an important role to design the like especially this prismatic bar. And that's what it is happening in the realistic way, that you see we have a different like in the building also, or in any of the uniform bar we have the different load applications are there, and under the load application how you see the deformations are there, which like which part of the beam is weakest, or which part of like the beam is the strongest, and how to calculate you see the different deformation at these things are really very important. And for that you see to define the stress versus strain relationship is also very important. So in that like the next segment, this all kind of analysis we are going to discuss. Thank you.